I have discussed this example in order to make you realize that in thinking of the possibilities of measurement in the space-time manifold, we must not confine ourselves merely to those minor variations which might seem natural to human beings on the earth. Let us make therefore the general statement that 4 measurements, respectively of independent types, such as measurements of lengths in 3 directions and a time, can be found such that a definite event particle is determined by them in its relations to other parts of the manifold. If P1, P2, P3, P4 be a set of measurements of this system, then the event particle which is thus determined will be said to have P1, P2, P3, P4 as its coordinates in this system of measurement. Suppose that we name it the P system of measurement. Then in the same P system, by properly varying P1, P2, P3, P4, every event particle that has been, or will be, or instantaneously is now, can be indicated. Furthermore, according to any system of measurement that is natural to us, 3 of the coordinates will be measurements of space, and 1 will be a measurement of time. Let us always take the last coordinate to represent the time measurement. Then we should naturally say that P1, P2, P3 determined a point in space, and that the event particle happened at that point at the time P4. But we must not make the mistake of thinking that there is a space in addition to the space-time manifold. That manifold is all that there is for the determination of the meaning of space and time. We have got to determine the meaning of a space point in terms of the event particles of the 4-dimensional manifold. There is only one way to do this. Note that if we vary the time, and take times with the same 3 space coordinates, then the event particles, thus indicated, are all at the same point. But seeing that there is nothing else except the event particles, this can only mean that the point P1, P2, P3 of the space in the P system is merely the collection of event particles P1, P2, P3, bracket P4, where P4 is varied, and P1, P2, P3 is kept fixed. It is rather disconcerting to find that a point in space is not a simple entity, but it is a conclusion which follows immediately from the relative theory of space. Furthermore, the inhabitant of Mars determines event particles by another system of measurements. Call his system the Q system. According to him, Q1, Q2, Q3, Q4 determines an event particle, and Q1, Q2, Q3 determines a point, and Q4 a time. But the collection of event particles which he thinks of as a point is entirely different from any such collection which the man on Earth thinks of as a point. Thus the Q space for the man on Mars is quite different from the P space for the land surveyor on Earth. So far, in speaking of space, we have been talking of the timeless space of physical science, namely of our concept of eternal space, in which the world adventures. But the space which we see as we look about is instantaneous space. Thus, if our natural perceptions are adjustable to the P system of measurements, we see instantaneously all the event particles at some definite time P4, and observe a succession of such spaces as time moves on. The timeless space is achieved by stringing together all these instantaneous spaces. The points of an instantaneous space are event particles, and the points of an eternal space are strings of event particles occurring in succession. But the man on Mars will never perceive the same instantaneous spaces as the man on Earth. This system of instantaneous spaces will cut across the Earth-man system. For the Earth-man, there is one instantaneous space which is the instantaneous present. There are the past spaces and the future spaces. But the present space of the man on Mars cuts across the present space of the man on Earth. So that of the event particles which the Earth-man thinks of as happening now in the present, the man on Mars thinks that some are already past, and are ancient history, that others are in the future, and others are in the immediate present. This breakdown in the neat conception of a past, a present, and a future is a serious paradox. I call 2 event particles which on some or other system of measurement are in the same instantaneous space, co-present event particles. Then it is possible that A and B may be co-present, and that A and C may be co-present, but that B and C may not be co-present. For example, at some inconceivable distance from us there are events co-present with us, now, and also co-present with the birth of Queen Victoria. If A and B are co-present, there will be some systems in which A precedes B, and some in which B precedes A. Also, there can be no velocity quick enough to carry a material particle from A to B or from B to A. These different measure systems, with their divergences of time reckoning, are puzzling, and to some extent affront our common sense. It is not the usual way in which we think of the universe. We think of one necessary time system and one necessary space. According to the new theory, there are an indefinite number of discordant time series and an indefinite number of distinct spaces. Any correlated pair, a time system and a space system, will do in which to fit our description of the universe. We find that under given conditions our measurements are necessarily made in some one pair which together form our natural measure system. The difficulty as to discordant time systems is partly solved by distinguishing between what I call the creative advance of nature, which is not properly serial at all, and any one time series. We habitually muddle together this creative advance, which we experience and know as the perpetual transition of nature into novelty, with the single time series which we naturally employ for measurement. The various time series each measure some aspect of the creative advance, and the whole bundle of them express all the properties of this advance which are measurable. The reason why we have not previously noted this difference of time series is the very small difference of properties between any two such series. Any observable phenomena due to this cause depend on the square of the ratio of any velocity entering into the observation to the velocity of light. Now light takes about 50 minutes to get around the Earth's orbit, and the Earth takes rather more than 17,531 half-hours to do the same. Hence, all the effects due to this motion are of the order of the ratio of 1 to the square of 10,000. Accordingly, an Earth-man and a Sun-man have only neglected effects whose quantitative magnitudes all contain the factor 1/10⁸. Evidently, such effects can only be noted by means of the most refined observations. They have been observed, however. Suppose we compare two observations on the velocity of light made with the same apparatus as we turn it through a right angle. The velocity of the Earth relative to the Sun is in one direction. The velocity of light relatively to the ether should be the same in all directions. Hence if space when we take the ether as at rest means the same thing as space when we take the Earth as at rest, we ought to find that the velocity of light relatively to the Earth varies according to the direction from which it comes. These observations on Earth constitute the basic principle of the famous experiments designed to detect the motion of the Earth through the ether. You all know that, quite unexpectedly, they gave a null result. This is completely explained by the fact that the space system and the time system which we are using are in certain minute ways different from the space and the time relatively to the Sun, or relatively to any other body with respect to which it is moving. All this discussion as to the nature of time and space has lifted above our horizon a great difficulty which affects the formulation of all the ultimate laws of physics. For example, the laws of the electromagnetic field and the law of gravitation. Let us take the law of gravitation as an example. Its formulation is as follows. Two material bodies attract each other with a force proportional to the product of their masses and inversely proportional to the square of their distances. In this statement the bodies are supposed to be small enough to be treated as material particles in relation to their distances, and we need not bother further about that minor point. The difficulty to which I want to draw your attention is this. In the formulation of the law, one definite time and one definite space are presupposed. The two masses are assumed to be in simultaneous positions. But what is simultaneous in one time system may not be simultaneous in another time system. So according to our new views, the law is in this respect not formulated so as to have any exact meaning. Furthermore, an analogous difficulty arises over the question of distance. The distance between two instantaneous positions, i.e. between two event particles, is different in different space systems. What space is to be chosen? Thus again the law lacks precise formulation, if relativity is accepted. Our problem is to seek a fresh interpretation of the law of gravity in which these difficulties are evaded. In the first place, we must avoid the abstractions of space and time in the formulation of our fundamental ideas, and must recur to the ultimate facts of nature, namely, to events. Also, in order to find the ideal simplicity of expressions of the relations between events, we restrict ourselves to event particles. Thus the life of a material particle is its adventure amid a track of event particles strung out as a continuous series or path in the four-dimensional space-time manifold. These event particles are the various situations of the material particle. We usually express this fact by adopting